Good morning and good afternoon, good evening, everybody, and welcome to another session of Expand Your Horizon. I'm very happy to have Chris Mowry with us today. Hi, Chris.
Hello, Shai. Thank you for having me today.
Yeah, our pleasure, our honor. Good morning. You dialing in from where?
From the U.S., from Atlanta, out the mountains of North Georgia in the United States. Springtime is arriving here.
I'm envious. So folks, Chris is the CEO of Type 1 Energy. Very exciting company, very exciting technology, which we at Orbia Ventures are fortunate to be part of that small part, very small part of that exciting journey. And we'll hear much more about it in the next hour. So Chris, thank you so much for taking the time. We know how busy CEOs are, and you in particular are facing some travels in the next few weeks. So thank you for freeing up 1 hour of your time and being with us today. So we will talk about nuclear fusion. We'll talk about the energy market. We'll talk about Type 1 and your exciting journey. But maybe before we do that, can you share with us a little bit about who is Chris, independent of Type 1 Energy?
Yeah, of course. Well, look, thank you for having me. It's been a long journey for me to fusion energy and Type 1. I was born in Spain, and my mother is an immigrant to the U.S. And I grew up with my head in the stars, so to speak. I wanted to be an astronomer, and I went to university to study astrophysics, and then decided I didn't enjoy staying up all night long. So I had to do something else in life, and picked up engineering. So I graduated from university with 2 degrees that seemed to have nothing to do with each other, engineering and astrophysics. But life is a strange journey, interesting journey sometimes. And where I am today is probably the only place you can go where the science of the stars meets engineering. So it's been quite a journey, and I've really had the opportunity in my life to explore the world in my journey through the energy business. I've had an opportunity to really work in every type of energy that exists, that people use today. Everything from traditional oil and gas to nuclear power to renewables, including hydropower. I ran GE's hydro business out of Norway. I've lived all over the world, and I've seen all the exciting things that are in the energy sector and all the big challenges. And I think both of those have ultimately brought me to where I am today at Type 1 Energy. So I'm not a fusion scientist. I always tell people that when I meet them in a business setting. So we have plenty of the world's best scientists in Type 1 Energy. I'm more of an energy business person and a very practical person when it comes to thinking about energy and how society needs to think about the future of energy in a more sustainable future. And ultimately, that is what fusion energy is all about. So I'm super excited to be here. A big part of my job is telling the story of fusion and also talking to people about the real challenge of the energy transition and trying to achieve something like net zero energy. And so that's something that is really part of my daily job, a big piece of what I enjoy doing. I like telling stories. And so I really welcome this opportunity, Shai, and do not at all feel like you're taking me away from my job. This is my job.
Thank you very much. Chris, yeah, you mentioned earlier to me today that you live by the mountains. What do you do when you're not working or traveling?
Yeah, well, I do have a life outside of fusion, believe it or not. One of the things that probably most people don't know about me is I climb mountains. I guess maybe now that I reflect on it, both literally and figuratively. So I've climbed some of the highest mountains in the world. and even some of them with my son. Everything from Kilimanjaro in Africa to the tallest mountains here in the U.S. In other places. But you know, fusion is like a mountain too, right? And energy is the last 300 years or so, the world has climbed a mountain of trying to figure out how to provide itself with the energy it needs. And I think it largely succeeded, but then found itself staring at a different mountain, which is how to create that energy in a sustainable way. So I guess maybe I'm drawn to the challenges of climbing mountains. And, you know, this fusion is a mountain. But the good news is that it's today we can see the top of the mountain, and we've done a lot of walking on this mountain over the past 50 years, and so it's really exciting to be, figuratively speaking, at high camp and getting ready and actually starting to walk up the last part of the mountain to the top. So that's the exciting part of mountain climbing. The not so exciting part is all the heavy lifting that it takes to establish your high camp. So that's maybe a good analogy of what we're doing. And you know, one of my biggest heroes is Maurice Herzog. He's the one of the first people to climb an 8,000 meter peak, Annapurna, and he has a famous saying that there are other Annapurnas in the lives of men, and I think that's a good thing to reflect and to maybe talk about more broadly as it relates to society, and that there are other mountains that society needs to climb, and one of them is the way to create a more sustainable future for energy, and that's the mountain I'm climbing, and that we're climbing here together at Type 1 Energy.
Amazing. So I ask my guests usually what are the two things Google doesn't know about you. So you mentioned climbing, and anything else that you feel comfortable sharing with us?
Yeah, I'm a student of language, and I like to write poetry. So
Wow.
yeah, it has the poetry maybe has nothing to do with directly with fusion, but I think it has a lot to do with communication. And like I said, that's a big piece of what I think a CEO needs to spend time on, is connecting the enterprise, the company, with the stakeholders that it has in all dimensions. And poetry is a way of communicating, and so maybe that's how this is all related.
Yeah. So you mentioned languages other than English, or probably Spanish. What are other languages?
And German, and believe it or not, I speak Swedish also, because I lived in Sweden for some time as well. So maybe not the most practical language, but a very beautiful language.
Nice. Yeah, thank you for sharing that, and give us a little bit of a sneak peek into your non-Type 1 life. So I think we can maybe switch gear and start talking more about Type 1 energy and the technology and the problem that it tries to solve. So let's switch into the main part of our session today and talk about fusion and Type 1.
Absolutely. So what problem are we trying to solve? We are trying to create a practical solution to the future of energy. The future of energy will most certainly be a portfolio of technologies in the real world. Obviously, there's a huge amount of focus today, and rightly so, around renewables. Renewable energy will be a big piece of the future of energy. So will storage. Energy storage is important to help deal with the intermittency of renewables, and I put into the bucket of storage things like hydrogen. Maybe overly simplistic, but hydrogen is not a source of energy, but it's a way of creating, storing, and moving energy from one place to another. But increasingly, I think there is acknowledgement in the world that in order to actually achieve, let alone try and maintain net zero energy, we need a new form of energy that is carbon-free, that is economical in the sense that it is cost competitive with other forms of energy like coal, and one that can be scaled. One way of thinking about what we need to do in terms of this kind of base load on-demand energy, the world needs to replace 40,000 coal-fired power plants that are running today. We're not going to replace that energy just with renewables. It's not possible. And that is the reason that people are investing in fusion energy. That is the reason that increasingly end users of energy are leaning in and working to pull fusion energy across the figurative goal line of commercialization. So that's kind of the big picture of what's going on here. And Shai, we can certainly talk about this some more later.
Yeah.
So why is everybody so excited about fusion? Fusion is the holy grail of energy. It is effectively unlimited in the sense that the fuel for fusion comes from seawater, the hydrogen in seawater. And one bucket of fusion fuel is enough to power a fusion power plant for a year. It's a technology that's inherently safe. It has nothing to do with nuclear power in any practical sense. And because of that, you can really think about using it wherever you need it. You can put it in places that aren't necessarily far away from society. It is on demand, as I talked about, and it also promises to be cost competitive with other baseload power generation that is today really fossil fuel. So those are all really compelling value propositions. So what actually is fusion? Fusion is the power of the stars. In some ways, it's the exact opposite of traditional nuclear power. If you think about traditional nuclear power, you think about splitting very heavy atoms like uranium, but fusion is the opposite. You take the lightest atom in the world, in the universe, hydrogen, and at conditions like those in the center of a star, you create the temperatures and the pressures needed to put those two atoms together and form helium. And through Einstein's special equation equals mc squared, if you weigh that helium atom and you compare it to the weight of the two hydrogen atoms, you find that helium weighs a little bit less. And that little bit of difference in mass times the square of the speed of light is a very, very large number. That is the energy that's released from the fusion process. So a little video here that maybe can talk a little bit more about this.
Hi, I'm Cami Collins, and I'm working to make fusion power a reliable, abundant, carbon-free solution to our long-term energy needs. But fusion can be confusing, so I'm here to answer your burning questions, starting with the basics. What is fusion anyway? Our sun is a ginormous fusion factory. Its raw material, hydrogen ions. Normally, two positively charged ions repel each other, but under the right conditions, hydrogen ions can overcome the repulsive force and fuse to make helium, plus a little leftover subatomic stuff. That together has less mass than the hydrogen that made them. That's because during the reaction, some of the mass from the hydrogen was converted into energy, a lot of energy. Here on Earth, we're building machines that will mimic the sun by fusing two different kinds of hydrogen isotopes called deuterium and tritium to make energy. Fusion is 4 million times more energetic than burning coal, oil, or gas, and a lot greener. So it could power our society for thousands and even millions of years. So check out our other videos for more answers to your burning questions.
So Chris, maybe just to say the obvious, and maybe not many people aware of the distinction. So the nuclear power plants as we know today, or the nuclear energy, is what we call fission energy, where you split atoms and create energy. Fusion is kind of the opposite. You merge atoms, and from that, energy is being generated. And it's a completely different technology, and you'll talk about it in more details, but it's cleaner, it's safer, it doesn't have all the negative considerations of nuclear fission, correct?
That's absolutely right. Absolutely right. So yeah, that's what Type Energy is focused on, this technology. So maybe we can switch gears here a little bit and talk actually about Type 1 Energy. Type 1 Energy, at least in its current form, came out of a conversation that I had with Bill Gates's Breakthrough Energy Ventures in late 2022, when they were looking at the Stellarator and other technologies that had evolved, and both themselves and the surrounding enabling technologies over the past 2 or 3 years. And we developed a thesis that by combining the right technology version of the Stellarator with the right team and building the right commercialization program, we actually had uniquely today an opportunity to take a direct shot on goal to commercializing fusion energy over the next decade. This is something that was not possible even 3-4 years ago. So it is an emerging opportunity built off of recent developments, both in fusion and in a set of enabling technologies. And that is fundamentally what Type 1 Energy is all about. So the technology that we are pursuing is called a Stellarator. So a Stellarator is a cousin of the much more common and ubiquitous technology called a tokamak, and both of these are called magnetic confinement fusion. And what that really means is that the fusion process, the plasma, which is the hot ionized gas, similar to what you would find in a star, is contained inside a magnetic cage. So a tokamak is a magnetic cage that's shaped in the form of a donut. It's a pretty simple design. It's very symmetric. The magnetic cage in a tokamak is made out of relatively simple 2-dimensional flat magnets that are wrapped around the short way and the long way of the donut. And importantly, in order to create the right kind of magnetic cage, the magnets need to be supplemented by a magnetic field that is created by a very, very powerful electric current that is driven through the plasma itself. We're talking something on the order of 10 million times what comes out of the wall socket in your home. And so this approach to creating a magnetic cage was initially developed almost 50 years ago and has really formed the foundations of most of the world's large science machines. And it turns out to be an okay technology for science, but as fusion has now shifted from its focus on proving the fundamentals of fusion science to developing a practical fusion power plant, the challenges of a tokamak have become increasingly apparent. They are inherently unstable, and primarily because of this large electric current that goes through the plasma. They also do not operate in a steady state fashion. They have to be operated most of the time in a pulsed version, and they're not very efficient because it takes a lot of power to drive this very large current in the plasma. So today, there is no clear path yet for a practical fusion power plant based on a tokamak. But people have known for as long as the tokamaks have existed that there is something called a twisted version of a tokamak called a Stellarator. And the idea was that if you could make just the right kind of twist, you could eliminate all of these challenges that a tokamak has. And in particular, you could develop a magnetic confinement fusion machine where the magnetic cage was only created by these external magnets. The magnets would have to be more three-dimensionally shaped, more complex, but because of the fact that you do not have any current circulating through the plasma, the machine is inherently stable and can also operate in a steady state condition, both of which are, of course, pretty important considerations in any practical power plant. And also they're much more efficient because you have very little recirculating power because you do not need to drive this electric current. So the challenge has been that nobody knew how to calculate this shape. And that's really what has changed slowly at first, about 15 years ago, but increasingly over the last few years. So this ultimately is what we are doing. We are taking the Stellarator technology and are commercializing it. So let me just say a few words about the company, and then we'll dive into the technology a little bit more deeply. In order for us to achieve our goal to design and build a fusion power plant, we need to think beyond traditional core focus on fusion science, and that really means we need to move beyond the traditional boundaries of the types of people that would work in a fusion company.
I think the Stellarator is really key here. That is the most robust, has the cleanest and clearest path towards fusion energy. Once we make it work, we'll have an energy source that just produces electricity and heat 24/7, requires very little in terms of fuel, and produces very little in terms of waste.
In Type 1 Energy, there's this culture that no idea is a bad idea, that really fosters an environment that allows you to be a better, more creative engineer. You're challenged, you're pushed to think outside the box, be more radical, and be more creative in how you solve these problems that have been a problem for decades now.
Chris, if I make a couple of questions for those of us that are not nuclear scientists.
Okay.
Plasma, is that the current of hydrogen atoms that are flowing in high speed, high temperature and collide? That's plasma?
Sort of. A plasma is a form of a gas where the atoms in that gas, if you will, are hot enough that the electrons are stripped away from the nucleus, and they basically move independently of the nucleus. So a plasma is made up of, if it's hydrogen, the nucleus of a hydrogen, which is a proton, that moves around independently from the electron that originally orbited it. So it's a very high temperature form of gas, kind of the fourth state of matter, where the electrons and the nucleus basically move independently of each other.
And this enables the collision that we talked about earlier, that enabled the energy generation?
Well, the thing that enables the collision is the very high speed or high temperature that exists in a plasma, because protons have electric charge. They're positive. They're kind of opposite of an electron, which is a negatively charged particle. Yeah. So just like when you try to push two magnets together, they don't want to touch. When you try to push two positively charged things together, they don't want to get close to each other. So you can overcome this repulsion force by moving them very, very fast toward each other. So that forces them to touch before the repulsive electric charge pushes them back apart from each other. And that requires very, very high combination of high temperature and high pressure. So on Earth, in the center of a star, temperatures are maybe 15 million degrees Celsius, and with a massive pressure somewhere on the order of 4 trillion atmospheres. Now, on Earth, there is no chance of making some pressure like 4 trillion atmospheres. So we compensate for that by increasing the temperature to something like 100 million degrees. So it's very, very hot. But that doesn't necessarily mean that it has a lot of heat content. So a good example that I always use is if you think about a match, which is quite hot, but you can actually extinguish a match with your fingertips without burning yourself because even though the temp match is very hot, it does not have a lot of heat content. It takes a lot of matches to boil a cup of water. So that's a good way of thinking about the difference between temperature and heat content. So in a stellarator, inside this magnetic donut, this plasma, which maybe has the volume of a large room, has 1 gram or 2 grams of gas in it, almost nothing. And if you think about what it takes to heat up that gram of gas to fusion temperatures to 100 million degrees, and you compare it to something that you're used to in everyday life, you think about a microwave oven. And if you want to boil a cup of tea in a microwave oven, which is maybe 150 grams or 200 grams of water, you put it in your microwave oven for 2 or 3 minutes. So imagine instead of that, you have 1 gram of water, and you heat that 1 gram of water, not with one microwave oven, but with 50,000 microwave ovens for a minute. That's how much energy you have to put into that 1 gram of water to heat it to 100 million degrees. And at that temperature, the electrons are stripped off of the hydrogen atoms, the protons, and they move independently. And because of that, they're subject to magnetic fields, electromagnetism, and you can hold that very hot, but almost at a vacuum density gas inside a magnetic cage. And that's the basic concept of a stellarator, is to create a magnetic cage, heat up gas to 100 million degrees where the electrons are stripped off the protons, and that ionized gas can then be trapped inside that magnetic bottle. And if you make a very good magnetic bottle, not a lot of that heat will leak out. And basically that process, once you start it, can basically continue on its own indefinitely as long as you keep adding fuel.
And this is the purpose of the very powerful magnets to create this confinement. So like electrons don't kind of like escape, right?
Yeah, electrons and protons don't escape. And so interestingly, the magnet in principle at least doesn't have to be that strong. If it's not strong, it cannot hold the plasma very tightly, and you need a very, very large machine. So the purpose of having a strong magnet is to hold that plasma in a denser configuration and let you make a practical sized power plant. But what's important about a superconducting magnet is that because a superconductor has no resistance to electricity, once you get the electricity flowing through the magnet and get the magnet to start working, you really don't need to add any significant energy into the magnet. So it doesn't really consume a lot of energy once it's energized, and once that magnetic field is created, that magnetic cage is created by the superconducting magnet. But the real key is, and we'll talk about this, is to design a leak-tight magnetic cage, right? Which means having just exactly the right shape magnet and the right placement of the magnet. That's where all the science comes in.
Thank you.
So let's move on here. Just want to say a few words about the company. I talk about climbing the mountain, and most mountains are climbed by teams of people. And it's important that a team works well together, especially when the mountain is steep and there's a lot of technical effort required to do that. So we have, as I talked about earlier, a pretty ambitious mission here, and that is to commercialize a practical fusion power plant over the next decade. And we want to be innovative in how we approach this challenge. And because of that, it's really important to focus on developing the right kind of culture in our company. That's something, as a leadership team, we spend a lot of time on. And so we have a set of values here that are boiled down to these 5 statements, but they're really around these words that I've underlined here. I think it's important that everyone has a sense of urgency the world has a big problem, as we all know, with climate change, and we need to get fusion over this goal line as fast as possible. It's important that all of us come to work and focus on this challenge with a sense of urgency. But we also need to do it in a very professional way while also operating in a very open environment where we bring in new ideas and creativity, and we cherish those things, and we embrace unique ideas from all different perspectives. So these are really important attributes to developing the technology solution, but we also need to deliver this. So balancing the innovation that we talk a lot about and the creativity is a real focus on execution and operational excellence. So it's that balance that creates a business that can actually take a great idea and deliver it to the marketplace. And that's really the kind of core set of values that I think define what our company is. So a little bit more about the Stellarator. As I mentioned, the Stellarator today has clear commercialization advantages over other mainstream fusion technologies. And that these advantages have been demonstrated now at large scale. So because of that, we have a direct path to final commercialization. And as we say inside Type 1 Energy, this is not a science project. That is not what we are doing anymore, but we're very much focused on taking a technology that works and making it better. And we can do that by focusing on a set of key enabling technologies that have just been developed more recently. But this pathway to demonstrating the Stellarator at large scale is something that's been taken over the past 20 years. As I mentioned earlier, the advantages of a Stellarator have been known for decades, but nobody knew how to actually design this magnetic cage that we've been talking about. So the first breakthroughs came through in the 1990s when the theory of modern Stellarators was developed. And a simplistic way of thinking about it is that this very complex shape is actually symmetric in a certain mathematical coordinate system. And that idea was developed by our Chief Science Officer, John Canick. And based on that, first in Columbia University and then in the University of Wisconsin-Madison, the world's first modern Stellarators were built at relatively modest scale. First in Columbia, which was almost a tabletop machine, and then at the HSX, helically symmetric experiment in the University of Wisconsin, a modest size but really full fidelity modular modern Stellarator was built that proved the concept that you could actually calculate the shape of this plasma. And when you did that and built a magnetic cage that held that plasma together in that shape, that the machine operated in a steady state condition and very stably. The Germans then took this predecessor, HSX, and scaled it up to power plant relevant size. We're talking something that's about 75% the size of a power plant, and applied the first generation superconducting magnet technology to that, and demonstrated definitively, starting with results that came out of the German research program in the 2018 to 2020 timeframe, that all of these attributes and all of these benefits of the Stellarator actually worked, and they worked at large scale. And this has really been the foundation for Type 1 Energy and has really moved Stellarators to the forefront of technologies that are ready for commercialization. Because as I shared with you earlier, the Stellarator does not have these fundamental challenges that a tokamak has that would still need to be solved for a tokamak to be used in a power plant application. But the Stellarator benefits really go beyond just the steady state nature of it and the fact that they're stable. But in the practical sense, in order to go deploy fusion power plant based energy generation around the world, you need you need to be able to have something that can be practically built and practically maintained. And one of the advantages of a stellarator is just one dimension of the practical advantages is that the that the stellarator magnets, as I mentioned earlier, only go around the short way of the donut. You can see here a module that was used to build W7X. And you can see the magnets here in the orange that go around the short way of the magnet. In a tokamak, they also go around the long way. And the long way is basically a circle that's on the order of 15 meters in diameter. And that's something that is too big to ship in any practical way. It obviously doesn't fit on a train car, which means you're basically reduced to trying to build this thing at the site of where you're going to create the power plant, or you need to build a power plant along the ocean or along a large waterway where you can send a barge. The stellarator magnet systems are small. They can fit on a rail car quite easily. And even though the shape of a stellarator looks random, it's actually made up of repeating half modules. The W7X machine was made up of 10 of these identical half-period modules, and our current design for a fusion pilot power plant based on this technology would be made out of 12 of these. So that really makes manufacturing something that is much more practical, because the whole thing isn't unique, but you're basically building multiples of the same identical assembly. And it also allows for modular maintenance, which is something that's really important when you think about the economics of a power plant. So what exactly is Type 1 Energy doing? As I mentioned earlier, we are going to apply a set of enabling technologies that have really emerged over the past 3 to 5 years to make this W7X machine, which worked, better, and in fact, make it good enough that it can be used in a power plant application. And so at the highest level, what we're really focused on here are 3 things. The first of which is to use modern high-performance supercomputing to basically use, as I say, a sharper pencil in calculating the shape of this fusion plasma and the resulting magnets that need to create the associated magnetic cage. The second is we are going to switch from first-generation low-temperature superconducting magnets to modern high-temperature superconducting magnets. And the third item is really to apply advanced manufacturing and 3D printing technologies to the construction and manufacture of this machine. And the Germans used traditional manufacturing techniques, and it took 10 years and $1 billion to build that science machine. One of the key elements for not only building the magnets, but the other components in a stellarator is in a practical way, is the application of advanced manufacturing. So we, Type 1 Energy, don't want to actually develop advanced manufacturing techniques ourselves, but we want to work with industry and use already commercialized technologies in a different way and apply them to the needs that we have. And we're already making good progress in this regard. And this is one of the key ways in which we're going to take cost and complexity out of the construction of the stellarator. Let me talk a little bit more about the team here. Obviously introduce myself. If you look across the middle row here, you'll notice a couple of the people that I previously mentioned, including our Chief Science Officer, John Canick, who really was the inventor, the discoverer of the modern theory of stellarators. And Thomas Pedersen was the technical lead at the German W7X large stellarator science experiment. So we got to get him to leave his job for life in Germany and come join us at Type 1 Energy. Our Chief Operating Officer, Ryan Guerrero, comes out of the U.S. aerospace and defense sector, where he ran a business unit for Northrop Grumman. And I think the list goes on here. So the point I'm trying to make here with this is that we recognize at Type 1 that we needed to build a non-traditional organization, something that you would not typically find in a startup, but a very highly experienced and accomplished business team that could partner with the world's leaders in stellarator technology to actually execute a program at the speed that we're talking about doing here. Of course, this all starts with the science team. I talked to you about John Kanik and Thomas Pedersen, but we've also brought in the former chief engineer of the U.S. fusion program as our chief engineer, Chris Hegna, who's the world's leading stellarator theorist, and David Anderson, who built the world's first modular stellarator at the University of Wisconsin-Madison. So between these gentlemen and the team that sits underneath them, they have had the experience of actually designing, building, operating, and maintaining stellarators. And really all of the world's modern stellarators have been built and designed by this team. So let me just stop there for now and open it up for questions.
Very interesting, very insightful. I hope I didn't interrupt too much with my simple questions. And there are quite a few questions coming in, so I'll try to curate the best ones. The first and quick one, people ask for permission if they can share the values of Type 1 with their teams inside Orbia. Would that be okay? It's not confidential, right?
You can absolutely share these values. I would hope that these are values that a lot of innovation companies have something that's similar to. So happy to share those.
Great. Now, related to some people when they talk about fusion, they mention the time that was achieved in a sustainable process. People talk about 1 second, 2 seconds, 3 seconds of operation. Where are we in that journey, and where is Type 1, and where do you want to be in the next year or two?
Yeah, so again, the real benefit for a stellarator, it is in many ways uniquely a steady state machine. And basically, once you turn it on, it'll just continue to operate until you turn it off. At W7X, you had to turn this thing off about a half an hour after you turned it on because they did not have enough cooling for the walls of the machine, right? And so it exceeded the cooling capacity. So, what we are doing in the design of our fusion pilot plant, of course, is making sure that there's enough cooling that we don't actually need to turn it off. But even back with the original CMT machine that was built in Colombia, that ran all day long. And I think Thomas Pedersen turned it off when he went home at night. So that is the real benefit of a stellarator, unlike other technologies, is once you turn this thing on, it just keep running. There's no set pulse length or anything like that. Yeah.
And so you mentioned heat management or cooling. Is that, well, two parts to the question, and I'm combining a couple of questions. First, is that a big issue, or it's not one of your top challenges that you need to solve? You think you can solve it? And then related to that, what are the main risks? We said in the beginning that it's risk-free, it has no downside like nuclear fission, but are there any specific risks that you foresee, and how do you plan to mitigate them?
Yeah, great question. So, look, with regard to cooling, there's no new technologies we need to develop. We just need to spend some time properly engineering this, and we'll definitely use additive manufacturing processes here because we're going to have an opportunity to put in some pretty sophisticated internal cooling challenges in the walls and things like this, where channels where we can run cooling water and other coolant in here to keep the walls cool. So the stellarator, from materials basis, the materials that exist today are good enough for a first generation fusion power plant. That's number one. And I guess that statement is a general statement in the sense that what is unique about our approach to fusion today is we don't see any binary risks. That is pretty unique. A lot of the risks we have are execution risks in the sense of being very careful not to try to develop new things that are not needed from an engineering perspective. Our focus is very much around minimum viable prototype product, right? It doesn't have to be, we're not designing a Ferrari here, we're designing a Volkswagen. And we need to be careful about staying focused on that. So we have another saying in the company, no new shiny objects. So, and maybe this comes from me because I'm not a fusion scientist. You know, my goal here is not to come up with the newest thing. My goal here is to get fusion commercialized. And that means the minimum number of new things I need to develop and engineer, the better. We're trying to minimize risk, not run after new shiny objects.
Yeah, great. You mentioned 40,000 coal plants as a reference to what we need to replace. How many stellarators would you, how many type 1 stellarators would you need to replace 40,000 coal plants?
Well, a stellarator, a full commercial stellarator is approximately the size of a traditional coal plant. So you can think of it as a 1-for-1 replacement.
It's a good market size for your, if you're successful.
It is. We will be successful as long as we're sufficiently humble and focused on execution. We will be successful.
Great. And people were also curious about location. Is there already a location in mind, or where would the first plant be built? People were talking about Tennessee, especially with the proximity to ORNL, and is that a consideration, or you're now working on a prototype and the commercial plan would be anywhere where the customer that will pay for it will decide that it wants the plant to be built?
Both of those are true. So as you could imagine, we'd very much like to continue our partnership with TVA and move beyond the engineering prototype to a first commercial pilot plant. You know, the Bull Run fossil plant in which we're going to be building our engineering prototype would be a perfect location. But really, in the end of the day, we're trying to solve a global problem. This technology needs to be deployed around the world, and we have no special reason why it would have to happen in the US or North America. And so, you know, we have started conversations in many parts of the world, and I think we're really looking for the best partner here to deploy that first pilot power plant. And I think our job in the next couple of years is to cultivate a set of good options, and then when we're ready at the end of 2028, we can hopefully make a good decision.
Great. And two last questions. I hope we will have time for both. The first one, with regards to maintenance or breakdowns, do you see that the new design of the stellarator also has some benefits in terms of when certain parts break down and they need to replace or maintain or continue operation despite the malfunction?
Yeah, absolutely. So, you know, this is more around parts of the machine wearing out. They won't last for 40 years for sure. So, you know, typically in a power plant, you'll operate for maybe 2 years, and then you'll shut down to do maintenance on the turbine and everything else. And so you really want to create a maintenance strategy where you can actually support the operation of a power plant for 2 years and do whatever maintenance activity you need to do on the machine inside a reasonably short period of time, you know, on the order of a month, let's say. And so this is where this modular half-period architecture that I talked about earlier really comes into play. So we're not talking about, for example, refurbishing the interior walls of this machine during the shutdown period. What we would do during the shutdown period is unbolt one of those modules, take it away into a maintenance shop, and take a spare and put it back in the machine. And then once the power plant is back up and running, then I have 2 years to refurbish that module that I took out and get it ready to go back in. So, if the machine is made out of 12 of these modules, we'll manufacture a baker's dozen, and so we have an extra one.
Nice. Okay, and last question. I don't know when you do your internal processing with yourself. Some people do it before they go to sleep, and some people do it when they take a shower or when they climb the Kilimanjaro. Okay, but what are the 2-3 things that keeps you really awake if it's before you're going to sleep, that you think, okay, these are the big things that I need to solve? I mean, you as type 1.
What are the big things that keep me awake? One is execution discipline. We talked about that a little bit. The second is building the right set of stakeholders. This takes everyone from the financial investors to partners on the supply chain. We have neither the time nor the money to invent everything here. And the thesis here behind type 1 is that in the world today, the technologies exist to commercialize fusion. So in some ways, we're like a weaver of a tapestry, and we need to find the threads and weave them together into this tapestry of solutions. So finding the right color threads, making sure we have the right weavers, those are the things we got to do at type 1.
Great. So with that, we're at the hour. I want to deeply thank you for the time and for helping understand such a complex technology in simple words. I and definitely all the people at Orbia really hope that this would become successful because we share the same ambition to save the world from pollution and emissions. So thank you so much for coming, and we wish you all the best.
Well, thank you, Shai. And as I mentioned to you earlier, hope is not a strategy. We do have a good strategy here, and it starts with good stakeholders and partners, and we are very appreciative of Orbia being one of our partners. So thank you for the opportunity to share the story with your team.